Okay, we will now use the equations we derived to look at exactly how large-scale ocean atmosphere circulations are set up in terms of these equations. So we'll look at what are called balanced flows. So main concepts will be geostrophy, Taylor-Proudman theorem and Taylor-Collins, and thermal winds. Okay, so the sections we saw, the zonal mean meridional sections we saw of winds and temperatures and so on, will begin to make sense now in these large-scale balances. So we will use our favorite hydrostatic balance, the ideal gas law, and so on to derive some special equations. But first we need to derive one of the most important dimensionless numbers that captures the concept of large-scale balance. Okay, here is our equation: du dt plus f z cross u, our Coriolis term, which can be expanded into partial u partial t plus u dot grad u, the advection term plus f z cross u. And when we do dimensional analysis, basically we look at a typical velocity. It could be wind, could be ocean currents scale. Let's say in the atmosphere it's about 10 meter per second, and in the ocean it's about, let's say, 1 centimeter per second. The typical time scale associated with it, obviously atmosphere is much faster than the ocean, and this then becomes u dot grad u. Remember, this is u du dx kind of term, so it'll be v squared over L, where L is x and y, so u du dx plus v du dy kind of term. So x and y horizontal scales, which are order 1,000 kilometers in the atmosphere and let's say 100 kilometers in the ocean, plus the Coriolis acceleration f cross fz cross u is just f times v. We know already the dimension of f and its magnitude. So a Rossby number emerges out of this, where it is basically the acceleration of the flow divided by the inertial acceleration f, right? Remember, f is radians per second, and v over L is basically meter per second divided by meter, so it's 1 over second. So you have a non-dimensional number called the Rossby number. And if we go back to our full equation, du dt plus 1 over rho grad p plus grad phi, right? Remember, this has got its centrifugal force included in there, and plus fz cross u equals friction. We will also add friction in this chapter and look at some flows that are without friction and some flows that do have friction. Okay, so we'll see those things. So phi here is our gravitational potential modified by the centrifugal force, right? We wrote that in the last chapter. Let's look at a few numbers then. V is order 10 meters per second, as I said. Horizontal scale is actually 10,000 kilometers, so 10 to the 6 meters, and the time scale is of an order of a day, so 60 times 60 times 24, it will give you order 25. These are order, so it's not a number, it's the order of 10 meters per second, order of 10 to the 6 meter, and order of a day. So V over T here is same as v squared over L in terms of dimension magnitudes, although that is 10 to the minus 4 meter per second squared. What are we going to compare that? So the acceleration is then compared with f, the Coriolis acceleration. In the mid latitudes, we'll see that r0 turns out to be about 0.1. Why is that? Because F, as you remember, is dependent on latitudes. Obviously, as you come closer to the equator, F becomes small, and on the equator, F is 0. So Rossby number is not very small in the deep tropics, right? So as you go to higher latitudes, F becomes bigger, and then you get this Rossby number being 0.1. So we will see what are the consequences of this Rossby number magnitude. What happens when it is small, and what happens when it's order 1. So let's say it goes from less than 0.1 to order 1. So we'll see how the flow changes based on the Rossby number. So essentially it's the acceleration compared to the Coriolis. If Coriolis dominates, then you get very different balances than when you have winds accelerating much faster than Coriolis. Obviously you can expect that on Earth Coriolis is going to be quite critical, so that's where the balanced flows or large scale balances will come from. Okay, that's what we are going to do in this chapter.